Hi everyone, I'm Gautam. I'm here with my teammates Ben, Sean, Utkarsh, and Harikesh. Today we are going to present a paper, a survey of approaches to secure high performance computing networks.
So, in the realm of HPC interconnects, speed is the goal, and security kind of takes a back seat because of techniques such as remote direct memory access. These techniques bypass the OS kernel to perform direct writes or reads in peer memory. And this is the case across InfiniBand interconnects, Slingshot from HPE Cray, Rocky, etc. But what if you have sensitive documents such as top secret information or HIPAA compliant information, etc.? We need to think of different approaches, and the three motivations in this presentation kind of cover those. So we take a look at encryption at the software level. We take a look at how we can redesign network primitives to include encryption at near hardware levels. And then we look at the use of technology such as trusted execution environments that are not originally used for HPC. So let's get started.
High performance computing relies on MPI to enable fast communication between the systems. However, traditional encryption methods often slow down the data transfers, creating bottlenecks. To address this issue, Crypt MPI offers a way to ensure security while minimizing the performance impact, making it suitable for HPC systems. Crypt MPI uses smart techniques to stay fast and secure. Pipelining overlaps encryption and transmissions. Multi-threading splits the workload across multiple cores, and the chopping algorithm handles large messages much more efficiently. Plus, there is dynamic tuning that adjusts settings based on the network to keep performance smoother, making it ideal for high performance computing. In conclusion, Crypt MPI delivers best of both worlds, security and speed. It's almost as fast as unencrypted MPI and far outperforms naive encryption. By using techniques like pipelining, multi-threading, etc., it handles encryption much more efficiently, making it perfect for high-performance computing systems. Looking ahead, Crypt MPI would support even more complex and large-scale HPC systems.
In this study, the networking technologies used are 10 Gbps Ethernet and 40 Gbps InfiniBand, and they have used AES GCM encryption scheme, and they have tested three encryption libraries: Boring SSL, Lipsodium, and CryptoPP, and they have used the benchmarks: encryption, decryption, ping pong, OSU micro benchmark, collective communication, and NAS parallel benchmark. The following two slides contains the performance details of three encryption libraries on the networking technologies 10 Gbps Ethernet and 40 Gbps InfiniBand with respect to various analysis metrics. The observations are as follows. In case of encryption decryption, Boring SSL outperforms Lipsodium and CryptoPP with minimal overhead, making it ideal for secure MPI communications. In case of ping pong, small messages perform well across the libraries, but Boring SSL shows the overhead of 78.3%, whereas CryptoPP incurs the highest overhead of 400%. In case of collective communication, Boring SSL is the most efficient for both the operations, while CryptoPP performs poorly for large messages with twice the timings. In case of NAS benchmarks, Boring SSL exhibits the least overhead, while Lipsodium and CryptoPP shows higher overhead, making them not suitable for HPC applications. In case of OSU multi-pair bandwidth, Boring SSL performs close to the baseline on both Ethernet and InfiniBand, while Lipsodium is moderate and CryptoPP struggles with large message sizes. It can be concluded that Boring SSL is the most optimal among the three encryption libraries, offering really less overheads and best suited for scalability, whereas Lipsodium and CryptoPP offers moderate and poor performances respectively.
So now we get into the realm of hardware level encryption, or as close to hardware as we can get. In Ethernet, we deal with sockets and packets, for some reference and background. In InfiniBand, we work with this notion of queue pairs, word queue elements, send receive queues, etc., which form the backbone of HPC-based communication. We cannot just use IPsec in these cases because the crypto protection used in them is unaware of RDMA headers, and we do not get the source authentication. A paper from Usenix ATC20 creates the notion of a secure, reliable connection in the InfiniBand standard, which utilizes symmetric cryptography under the hood, and the use of RDMA-based NICs or RNICs, which are already common. So here are a subset of the designs featured in SRDMA. First, above all, we assume that the RNIC is trusted, which enables us to perform packet authentication, payload encryption, decryption, and trusting of the internal bus. SRCQPs contain two big things. First, we have a secure transport header, which features this MAC header, featuring a routing header, a base transport header, and a nonce. The nonce is just a packet sequence number, which allows us to avoid repetition based on certain assumptions for the next 3,000 years, per the paper's assumptions at least. The calculation here allows us to authenticate the MAC address, and this prevents source address spoofing on top of already placed InfiniBand memory protection. Packet authentication is already straightforward. We can offload crypto operations to these RNICs, or particularly these smart NICs, which are just system-on-chip systems. And in particular, we look to avoid memory overhead. Instead of putting each metric key at the queue pair level, we put it at the protection domain level, which already protected memory regions in IB semantics. And this allows us to reduce our memory footprint that much further than before. So the results of SRDMA are pretty astonishing. We see kind of reasonable overhead if we use only protection domain PD protection. External memory protection gets a little bit worse depending on the encryption algorithm and what we're using. And then the combination of them, depending on, again, the encryption algorithm, will either get further minimal overhead or sometimes a little bit more. But everything across these basically shows that putting near hardware encryption into a smart network card, such as NVIDIA's Bluefield smart NICs, and through the use of the SRDMA protocol, we don't have to sacrifice too much bandwidth or latency for extra protection. And we also get a decently small memory footprint compared to other state-of-the-art models, such as your classic RDMA, IPsec, variation of TLS, and some other references, which, while they provide a smaller overhead, they don't support secure communication or the InfiniBand architecture, for example.
Data security is crucial, especially in high-performance computing. There is a significant advancement in this domain with the integration of Intel Software Guard Extension (SGX) with HPC workloads. Intel SGX uses instruction codes to create a trusted execution environment that allows user-level and operating system code to define enclaves. When enclaves leave the CPU, SGX encrypts their contents using keys stored in the silicon. This paper explores the performance implications of running high-performance computing workloads with Intel SGX technology. Historically, SGX faced several limitations such as small enclave memory and the need for code modifications, making it less suitable for HPC workloads. However, two significant advancements address these challenges. The introduction of Intel's third-generation Xeon scalable processors, which support up to 1 TB of enclave memory, and the Grameen 1.0, a library OS that allows unmodified applications to utilize SGX. To evaluate performance, the authors used microbenchmarks to analyze core performance, memory bandwidth, and latency. The key findings were in core performance and memory bandwidth, there were performance slowdowns observed from 4% to 17%. In case of memory latency, especially with sensitive workloads, there was an increase of 170% in latency. Overall, the average performance slowdowns were observed from 1.5 times to 4.4 times. However, this improved significantly compared to prior studies reporting 1.2 times to 126 times slowdown. In conclusion, the combination of third-generation Xeon processors and Grameen reduces performance overhead for SGX-based high-performance workloads significantly. The advancements make SGX a more practical option for secure and high-performance computing, especially in HPC environments. Latency-sensitive applications still face performance bottlenecks, requiring further research and optimization. Grameen plus SGX provide a promising solution for organizations needing robust security without excessive performance sacrifices. The study paves the way for further optimization of secure high-performance framework and highlights SGX potential for real-world application. The result underlined the need for targeted improvements in areas like memory latency in high-performance workloads.
For the final section of this presentation, we will be discussing scientific computing workloads on general-purpose TEUs, or Trusted Execution Environments. Let's begin by talking about AMD SEV. This technology is designed to protect data confidentiality and integrity by encrypting memory at the hardware level. However, research highlights two key challenges when using AMD SEV in high-performance computing environments. First, AMD SEV requires careful memory placement on systems with large-scale NUMA, or non-uniform memory access machines. Without this awareness, workloads can experience a performance slowdown ranging to 1 to 3.4 times. However, when NUMA-aware placement is applied, slowdown is significantly reduced, staying close to a minor 1 to 1.15 times. Second, SEV relies on virtualization, which introduces additional performance challenges. For workloads with irregular memory access patterns or large working sets, this can result in slowdowns up to 4 times compared to native execution. Now, moving on from AMD SEV, we're going to talk about Intel SGX, or Software Guard Extensions, and how it compares to the SEV for high-performance computing workloads. One major challenge with the Intel SGX is its limited secure memory size and rigid programming model. These constraints make it less suitable for many HPC workloads, especially those requiring large datasets or complex computations. When running unmodified HPC workloads, SGX demonstrates significant performance degradation. These slowdowns range from 1.2 to an astonishing 126 times, depending on the workload. In contrast, AMD SEV, when configured correctly, performs much better. It offers sufficient protection against HPC threats while introducing only minor performance overheads. The first table outlines the hardware configurations used in this experiment. Figures 3 and 4 illustrate the performance impacts of AMD SEV for the NAS parallel benchmarks. The results compare 3 configurations: native execution, QEMU virtualization, and QEMU plus SEV. In both graphs, QEMU plus SEV shows notable performance degradation compared to native execution due to SEV-specific NUMA memory allocation restrictions. Applying interleave NUMA allocations significantly reduced the performance gap between QEMU and QEMU plus SEV, recovering most of the lost performance. Figures 6 and 7 compare the memory allocation over time using the default and interleave NUMA memory policies, with and without SEV enabled. The comparison highlights that interleaving memory allocation significantly improves performance in both SEV and non-SEV configurations, particularly in multi-node systems. In conclusion, HPC workloads still need a lot of security on their own. Different solutions at the hardware and software levels provide similar benefits with their own multitude of constraints. Some final important questions that have still yet to be answered are: can we mitigate the overhead further? Can we adapt IPsec for HPCs? And can we develop novel hardware or preserve everything in software? We hope you've enjoyed our presentation.